Good afternoon. Hope you had a good Splash 2022 experience, and I hope this will be a good way to end the conference. This is joint work with my collaborators Amrit Kumar and Ilya Sergey, and the paper for this was published at PLEI 2021. So if you're interested in any of the details, do check that out. The title of this work is quite a mouthful, so let me give you some intuition for what we are doing. And there is a bit of background necessary to understand what it is that we are actually doing. First of all, we are using formal reasoning techniques in this work, namely static program analysis, but not in the way static analysis is usually used in the blockchain world, and the way we've seen in the previous talks, that is to verify the correctness of contracts or to establish the absence of certain classes of bugs. That is not what we are doing. Rather, we are using static program analysis for scalability to improve the execution performance of smart contract transactions, so not for correctness. Secondly, we use static program analysis to enable smart contract sharding. So our analysis is not part of, say, the compiler that generates bytecode from some high-level language. In some sense, our analysis is part of the consensus protocol itself, and it is used by the consensus protocol to determine a better way of splitting the transactions across the nodes for processing. Well, I guess this is informally the blockchain and smart contract session, so I expect everyone knows what the blockchain is. What you might be somewhat less familiar with, especially if you don't work in the area, is some of the challenges that come with scaling blockchains. And there are two big challenges. These are not the only ones, but these are the main ones. These are state bloat and execution throughput. These are the main challenges. So the way typical blockchain architecture works is there's some kind of network of nodes, and users send transactions to this network in some fashion. And the way typical blockchains work is each node, in order to be able to process transactions, must store the entire state of the system. So a transaction might require any bit of the current state of the system. So to be able to process any transaction, you need to have that state available in case the transaction requires it. And again, the way these systems work, typical architectures work, is the nodes don't trust each other. So each node has to execute every transaction in order to get the result of executing that transaction and validate that the other participants in the network have kind of done it correctly. You can't just trust other people to do it correctly. You must verify. Now, that works as far as it goes, but it has this problem that adding more nodes to the network doesn't actually increase the capacity of the network. In fact, it actually slightly decreases due to like bandwidth constraints. And in particular, adding more nodes does not increase throughput in a typical blockchain architecture, and it does not allow more state to be stored. And this is a big problem in practice. So I have some numbers as of November last year. As of then, Ethereum's head state, so this is just the current state of the Ethereum memory, so to speak, was 130 gigabytes. So this is what you need to store in order to be able to process transactions. So this is not any historical data. This is just the state at the head, at the tip of the chain. And if you want to execute transactions quickly, you would want this to be kept in RAM, but 130 gigs is quite a bit of RAM. So in practice, this is stored on disk, and you do actually need a very fast disk to be able to run an Ethereum node. So state bloat is a problem. We would want to keep everything in RAM, but having too much state prevents us from doing that. The other problem is execution throughput. So in this monolithic blockchain architecture that I've described, execution throughput is limited by the capacity of the least performant node in the network. In some sense, you're reaching agreement amongst a set of nodes, and all of the nodes need to execute every transaction. And that means that you kind of need at least a supermajority of nodes to keep up. So you are limited by these lowest node in that supermajority. So one way to kind of scale blockchains is to increase the node hardware requirements. And some blockchains do this. So Solana is one blockchain that goes kind of all in on this big node idea. And to run a Solana validator now, you already need more than 256 gigs of RAM to keep all the state in RAM. You need like 32 cores. You need 1 gigabit internet connection, download and upload. So that's one way of tackling this problem. The other way, that is the one that is relevant for this talk, is called sharding. So rather than keeping this monolithic architecture, you split the network, the nodes in the network, into subsets of nodes called shards, and then you have each of the shards execute a subset of the transactions. And there are blockchains that do this already, and the one we built our prototype on top of, Zilliqa, is one of them. So these blockchains do execution sharding, but not strictly speaking, state sharding. The problem with these blockchains is they take a very naive approach to sharding smart contracts. Concretely, what they do is they assign the contract, every contract, to a particular shard, and then every transaction that interacts with that contract is processed by the nodes in that shard. Now, the problem with this is that if you have a contract that is very popular for whatever reason, at some point, the nodes in that shard will get bottlenecked. They will no longer be able to keep up with the transaction workload. And other users of contracts in that shard will have a hard time getting the transaction true, and that's a bad experience. And the problem is that the rest of the network is not doing anything in this example. Okay, we have spare transaction processing capacity, which is not using it. And this is the problem we are solving. Can we somehow improve the utilization of the transaction processing capacity in the sharded network? What we would want to do, kind of conceptually, is we would want to somehow replicate this contract across all of the shards and have each of the shards process a subset of the transactions touching this contract. Now, we can't kind of do this directly because we still want this contract from a user perspective to behave as if it was a single contract. So we still want transactions to have kind of sequential semantics, and what a transaction in this shard should know what's happening in that shard, and so on. Right? So we can't just like clone the contract. We need to be a bit more clever in how we do this. So how can we do it? Well, the idea is, so the problem here is that the blockchain doesn't know how to shard the contract because it doesn't know what the contract is or does. For the consensus protocol, the contract is just a black box. It's some code and it's some state. But the blockchain doesn't know, or at least the consensus protocol doesn't know the meaning of the code or the meaning of the state. So how can we shard contracts? Well, the idea is to not treat them as black boxes. So we can have the consensus protocol look at the contract's code to learn how to shard it. And we use static program analysis to understand what the contract is doing at some level. So to reiterate, we are solving this problem of smart contract sharding. And we are applying the technique of static program analysis to tackle this problem. And in particular, we have two different kinds of analyses, ownership analysis and commutativity analysis. And I will explain this shortly. So let's look at an example and see exactly what the blockchain does. So we've said the blockchain looks at the contract to figure out what it's doing to learn how to shard it. So here's the contract that was giving us trouble earlier, this orange my token contract. And this is kind of like an artificial example. So if you're into blockchains, this isn't really, it is kind of a merge of two different contracts. But it serves to illustrate both parts of the analysis in a single example. So this contract keeps track of user balances of some token for 3 people, Alice, Bob, and Charlie. And you can do 2 things with this contract. You can buy some tokens with the native currency of the blockchain and get some of these contract tokens in exchange. And you can transfer tokens between users. So how can we shard this contract? Well, the idea is, rather than keeping all of the state for the contract in a single shard, we can split, or logically split, if not physically, logically split the state across all the 3 shards, right? And then the blockchain, the consensus protocol, can look at the code of the contract and the code of the transitions, in particular here, this buy tokens transition, and realize that the only piece of state this transition touches or relies upon is the balance of the buyer. So if Alice is buying 5 tokens, then we can process that transaction in Alice's shard. And similarly, if Charlie is buying tokens, we can process that transaction in Charlie's shard. And the reason we can do this is because now the consensus protocol, seeing the transactions and knowing which contracts they invoke, knows that these transactions will touch different portions of the state and they can be processed in parallel. And what enables this is our ownership analysis. Now, that's fairly straightforward. What about more complex transactions? So here's an example. We have 2 transactions, Alice transferring 5 tokens to Bob, and Charlie transferring 3 tokens to Bob. Now, quite clearly, these transactions are not independent. They both modify Bob's state. And moreover, these transactions touch the state of multiple shards. Can we still execute them in parallel? And the answer is yes. In fact, we can. And the reason we can execute these transactions in parallel is because they have commutative effects. In particular, the effect of these transactions is to set Alice's balance to 6, set Charlie's balance to 9, add 5 to Bob's balance, and add 3 to Bob's balance. And these effects, these 2 commute because they touch different portions of the state. And these 2 effects commute because they express a commutative operation. So what we can do after executing these transactions in parallel is we can merge or join these effects to obtain the kind of cumulative result. And then we can apply that result to obtain the final state. And what enables this kind of reasoning is commutativity analysis. Right. Okay, so that was a fairly long introduction to give you a flavor of what we are doing. So now I'm kind of going to restart the talk and give you the technical meat, or at least some of the technical meat. So we build our tool, which we call CoSplit, on top of the Zilliqa sharded blockchain, which uses the Scilla smart contract language. Scilla is a language inspired by System F. It's a language for writing smart contracts, very heavily based on System F, and heavily inspired by the notion of communicating automata. So smart contracts in Scilla are not objects directly, they are automata in the automata theory sense. And these automata have state and they have transitions. And transitions in Scilla are atomic, there's no reentrancy, so they really are transitions, not method calls. And there are 2 key features of Scilla that we kind of rely on in this work. And one of them is that Scilla contracts clearly separate computation from communication. In particular, communication between contracts in Scylla is not represented as method calls, but rather as explicit message passing. And messages are only sent after the end of a transition's execution. Right. The other feature we rely on is that Scylla has a very strict distinction between pure computation and effectful computation. So Scylla Scylla contracts are mostly pure. There's a very small imperative fragment that is used to update state, but this fragment has no loops or recursion. So all kind of tricky bytes to verify are in the pure fragment. So in particular, only pure non-effectful recursion is allowed. I think in a more recent version of Scylla, this has been changed, but at least at the time, this was the case. And what this means is that we can have fairly fast and fairly precise static analysis because we don't have to worry as much about loops. Okay, so here is an example of what Scylla code looks like. At the top of the slide is a state declaration. So very similar to what we've seen before. This implements a ERC20-like contract. Well, it's a fragment of a ERC20-like kind of currency token contract. And the key piece of state in this contract is this mapping called balances that maps user addresses to their unsigned integer balance. And this is a fragment of the transfer transition of the contract. So this transition has two parameters: the recipient we're sending money to, the amount we're sending, and there's an implicit parameter _sender. You don't really have to go look at this code in detail because we will look at it in detail in a couple of slides. But this is just to give you a flavor of what Scylla code looks like. Okay, so what do? Well, we look at a code, right? We have the blockchain look at a code and statically analyze it. And we produce kind of two artifacts. First, we produce an effect summary for every transition. So we analyze every instruction in every transition, and we produce a summary of over-approximation of the behavior of this transition. So for example, an effect summary might say that this transition reads from that field, say the balance of the sender, it writes to that field, it conditions on this value, it potentially sends a message to another contract, and so on. Right, and this effect summary over-approximates the behavior of the transition. And because we don't have imperative loops, this is quite easy to figure out what the effects of a transition are, because pure computation is non-effectful. Okay. And this effect summary is sufficient to enable the ownership reasoning I've shown earlier. We can tell from the effect summaries whether two transitions depend on fields that potentially conflict. And if they do, then we can't execute them in parallel. Now, the trickier bit is commutativity. And here we build a linearity-aware flows-to analysis that is very heavily inspired by GSC's cardinality analysis, which was published at Popple 14. And we express this analysis as a type system for contribution types, or we call them abstract expressions. And the idea is these describe what values look like. In particular, well, I will explain it on the next slide. And the way this is used is the effects in the effect summary are annotated with these contribution types to describe not just which fields are written or read from, but which values are written into the fields. And it is these contribution types that let us determine when effects commute. So here's the domain of the analysis. It's kind of simplified. I guess, most important part, or most interesting part at least, is this notion of abstract expressions, or what I called earlier contribution types. And what a contribution type is it identifies sources of values, either transition parameters or program fields, and it identifies, so there's the first argument there, it identifies how those values flow into other values. In particular, do they flow linearly into other values, or do they flow in some linear, non-linear fashion, or perhaps they don't flow at all into other values. And then which operations, primitive operations, are applied to a contribution source to obtain a value. I will show an example of this. It's a lot easier to understand with an example. And then the effect summaries describe what a transition may do. It may read from some field, it may write some expression, abstract expression to some field, it may accept some native blockchain funds, it may condition on some value, may send a message, and so on. Okay, so here's the example code we looked at earlier. This is, again, the transfer transition. It's somewhat simplified, but not too much. The transfer transition of ERC20-like contract written in Scala. So there are two arguments to this transition, the address of the recipient and the amount of tokens we're transferring. And there's an implicit argument for the whole transaction underscore sender, which is the sender, the originator of the transaction. So let's proceed through this code kind of line by line in the same way the analysis does. The second line there reads from this mapping balances at the key sender. So it reads the balance of the sender, and it binds that value to this binder from val. And that is the effect that is associated with this statement, which is we're reading from balances sender. And then we condition on this value, and based on whether this value exists or not, here I'm only showing the case where the sender actually exists. We do send the money. So what's happening here on line 4, we are creating a new binder in the match statement, and this binder val, and over there you see a contribution type. So what this is saying is that the value of val is described as the initial value of balances sender at the beginning of the transition that flows linearly into this binder val, and it has no operations upon it. And then we condition on balance and sender and amount. And again, amount is an immutable transition parameter. And if the sender has enough money, we subtract the amount we're sending from the balance of the sender. So if you look at the contribution type here, is balances sender flows into this value, mu from val, linearly with the subtraction operation applied to it, and amount flows into this value linearly with the subtraction operation applied to it. And then we write this value described by this type into balance and sender. Right? And then the balance of the recipient, we read that, we kind of update that. I'm not showing the contribution type there directly, but then we write the balance of the recipient, and here's the contribution type for that. The value of the recipient is obtained by the previous value, flowing linearly with addition applied to it, and the amount flowing linearly with addition applied to it. So on the right, all the things on the right, the things in blue are form the effect summary for this transition. And this describes at a high level what the transition does. And this is what the blockchain processes. And then we compile these effect summaries. So we produce an effect summary for every transition and contract, and we compile, in some sense, these effect summaries to constraints that tell us when a transition might be executed soundly by a particular shard. Now, I don't give the details in the talk. You'll have to read the paper if you're interested in the details. But here's a kind of flavor of what's going on. You have there on the left the constraints that a shard might need to satisfy to soundly execute this transaction in parallel with other transactions. And on the right, you have the effect summary that we saw earlier, and I've kind of neatly divided it into two portions. So basically, there are two fields that are touched here: balances sender and balances to. And the interesting bit is that here, for this effect summary, well, to be able to process a transaction that uses this transition, you need to own balances sender, but you don't actually need to own balances to. And the reason you don't need to own it is because the operation that is actually performed on balances to, the effect, is an increment. It's not just plainly addition, it's an increment, and increments from different threads commute under certain conditions. And in particular, this analysis only kind of like, as was perhaps observed in the earlier talk, this kind of reasoning only applies if at runtime sender and to are actually different values. Right? And we use this information that this is kind of expressed as a commutative operation to describe how contributions from different shards are merged. There's this notion of weak reads that appears here. You'll have to read the paper for the details. It's quite interesting. What's happening is that I am a sender, and I might actually have more money than I think I do because someone is sending me money in parallel. But you'll have to read the paper for the details. Okay, so to finish off, we integrated this with a running blockchain. So this is not in production, it's only a prototype. The way it works is we run the static analysis when the contract is first deployed. We store the resulting sharding signature. So these are the transition constraints and the instructions of how to merge contributions from different shards for each field in the contract. And at runtime, when processing a transaction, the blockchain looks at the transaction, figures out which shard, if any, satisfies the constraints to process that transaction in parallel, and allocates the transaction to that shard. And if no shard satisfies the constraints, then that transaction must be processed sequentially in the usual fashion. And after the parallel processing, we merge the contributions from all the shards before proceeding. So in summary, we built a kind of parallelizing compiler for blockchains where the execution fabric is the sharded structure itself. Okay, and we evaluated this. The evaluation is in the paper. It works fairly well for certain kinds of contracts. It doesn't really do much for other kinds of contracts. But where it doesn't do much, the overhead is quite low. So it's not much of an impediment there. Okay, that is all. I'm happy to take questions.
Regarding the, I think it's page 13, so you actually sharding the addition into different, right?
Mm-hmm.
So the question is regarding the addition might be causing an overflow problem, right?
Yes, so, yes.
Yeah, you've got two transactions sharded, so which transaction are you going to revert?
Yes, so the principal solution for that is to not have overflow. What you can kind of do is, yeah, we don't really have a practical way. If you actually do have overflow, you have to be very conservative in terms of how many kind of like transactions you allow. So we don't have a very good story for that.
You have to have a prerequisition of the final result.
Yeah.
Not really.
Yeah.
So the second one, I think this is more like into the concurrent execution of transactions rather than the sharding, because I haven't seen anything that is related to sharding. Then regarding the concurrent execution, then why don't you have to like shard the transaction to different distribute the transaction to different shards instead of having a
local. Yeah, so you can use the same analysis.
I think that one you will save lots of storage loading time. So I guess.
Yeah, so you can actually do both. So you can use the exact same analysis to parallelize transactions locally within a single shard, and then you can also use the same analysis to parallelize across shards if needed.
Well, I would doubt that the sharding solution will be having a performance gain because usually the balances contains all the addresses. I mean, you always have to load the whole balance rather than a particular address. So I do not see a performance gain there. But anyway, that's architecture.
Yep.
I guess the opposite question of the overflow. How do you define exactly commutativity? Like imagine that 0 gets like 5 from somebody, 5 from somebody else, but sends 5 to somebody. It seems like everything commutes, but you could basically have 0 plus 5 plus 5 minus 5. But if you start with the minus 5, Bob at some point has a negative balance. Do you know what I mean?
I get the kind of overall thing you're saying. So the fact that every, so this is a kind of extra slide that I have, the fact that every operation in a set of operations is commutative does not imply necessarily that the overall effect is commutative. Yes, we do take that into account. And I mean, the details of how we do that are in the paper.
So do you check commutativity pairwise?
Between transitions, yes.
I'll have to read the paper.
Yeah.
All right, well, I think we've come to the end of the session. Thank you very much.